Thanks for inviting me, and it's great to be back here. It's been a few years since I visited Princeton. So this is joint work with Semeredi, who's my former PhD student and now at Rutgers, Sohail Benedad, who's at Northeastern, and Huan Lee, who is a current PhD student working with me. So just a very quick reminder of the definition of the problem. That's the focus of this talk, the maximum matching problem. So matching in a graph is any collection of vertex disjoint edges, and the maximum matching problem is to find largest matching in a given graph. So in this example, the red edges form a matching, and they also happen to be forming the largest matching in this graph. So this is an extremely well-studied problem, and in the classical setting, where the algorithm has random access to the input graph, and the input graph is a static graph. It's not changing, it's fixed. In fact, new results keep getting added to this rich history of this problem. There have been several breakthroughs on the matching problem in the just last a few years alone. The focus of this talk is going to be matching problem into relatively modern setting. The first one is going to be the setting of the streaming model, where the algorithm no longer has random access to the input graph. So we take away that property. And the second one is the dynamic model, where the underlying graph is no longer static, but it will be undergoing updates. Okay? And we want to maintain a large matching. And throughout my talk, I'm going to follow the convention that n will denote the number of vertices and m will denote number of edges. Okay, so let me start by saying a little bit about what's known about this problem in each of these two models. So let's start with the streaming model. So here the input graph is presented as a stream or a sequence of edges. And the algorithm sees the graph revealed in this sequence, but it has limited memory, typically distinctly smaller than the space needed to store the entire graph. So it can look at this sequence of edges passing by, store some information about them, and then at the end output a solution. Okay, so the algorithm no longer has random access to the input graph. So our goal here is to try to compute a near optimal matching using small space in a single pass over this tree. So formal study of this problem is started almost 20 years ago in the work of Feigenbaum and others. And they pointed out two very simple solutions to this problem. The first one is you can, of course, store the adjacency matrix of the entire graph, and then compute at the end the maximum matching exactly. And this would take order n square bits of space. The second one is you could maintain a maximal matching, and which is going to give you a half approximation to the problem. And this will only take order n log n bits of space, because all you need is to store your current maximal matching. And whenever you'll see a new edge UV, you just check, are U or V already matched in the current matching? If neither of them is matched, you are going to add this edge UV to your solution. So all you need is the space needed to store the solution. In the same work, they also showed if you want to compute the matching solution exactly, you want an optimal solution, then you need indeed omega n square bits of space. You can't shave off anything for computing an exact solution. Now, since this work of Feigenbaum et al. In the years that followed, some other barriers have been discovered in terms of how much space do we need to compute good approximations to the matching problem in the streaming model. In particular, about 10 years ago, we discovered a connection between the problem of approximating matchings in streaming model and a very fascinating class of graphs called the Ruzsa-Szemerédi graphs or RS graphs. And I will explain this class of graphs towards the end of my talk. And with this connection, it's not difficult to show that any algorithm that gives better than 2/3 approximation for matching problem requires distinctly more than n polylog n space. So the exponent there is not quite n to the 1 plus delta for some constant delta greater than 0, but the total space is distinctly more than n polylog n, which is what we typically hope for many of these graph problems in the streaming model. And this connection was further refined, and our understanding at this point is that any algorithm that gives you better than 0.59 approximation already requires this much amount of space at least. Okay? And these bounds could turn out to be stronger than what's being mentioned here because they depend on the density of these RS graphs. And I'll talk about this a bit later. Okay, so quick summary. Exact solution basically can be done in theta n squared space, half approximation in order n log n space, and then we have some barriers on how much space you need, even for beating 0.59 approximation. But even with all these barriers, the following remains a completely open problem. Is there a streaming algorithm that can find better than a half approximate matching in small O of n squared space? I mean, ideally, we would like it to be better than n squared by a polynomial factor, but can we just beat factor half and short of storing the entire graph? Okay, so that was a summary for the streaming model. And then the second model that I'm going to talk about is the setting of dynamic matching. So let me just briefly summarize what we know here. So here the setting is that the graph is undergoing insertions and deletion. And after each update, we need to output a near optimal matching in the graph. And what we're hoping to do is avoid recomputing the solution. We want to be able to respond to every update much more quickly than recomputing. So I want to start by showing you a simple folklore algorithm for this problem. And this will give us a benchmark that's going to be useful for us to keep in mind. So here is a very simple algorithm for dynamic matching, for maintaining near optimal dynamic matching. Suppose you currently have a 1 minus epsilon over 2 approximate matching in your graph. And let's call this matching M. For the next epsilon m over 2 updates, basically I'm going to ignore any insertions which happen. And if you have any deletions, I will, and which are deleting any edges from the matching that I have computed, I'll remove them from my model. So I'm just going to output this M modified according to these changes as my solution for the next epsilon m over 2 updates. It will remain a 1 minus epsilon approximate matching during this. At the end of this, I'm going to recompute a 1 minus epsilon over 2 approximate matching in the current graph, and this can be done in time, which is order m over epsilon. Okay, so let's see how much time we are spending per update. So number of edges in the graph can be no more than order n times cardinality of m. Basically, all the edges in the graph are incident on the endpoints of the vertices that participate in a maximum matching. And so you can bound the number of edges in terms of the size of the largest. And then it's just a simple calculation. The work we did divided by the total number of updates gives us the update time. The time we are spending per update is bounded by order n over epsilon squared. Okay. So that's what you can get for maintaining a 1 minus epsilon approximate. What else is known about this problem? Well, quite a lot. Okay, it has been a very active area of research over the past 10 years or so. So if you're willing to settle for half approximation, in fact, it's possible to design algorithms whose update time is just 4 tilde 1. But if you wanted better approximations, so the next interesting milestone appears around 2/3 approximation. There is a shift in complexity, and the best known algorithm takes m to the 1/4 time per update. And actually, this algorithm uses a beautiful data structure which has since been used in many other matching problems called EDCS. Lastly, an important result for us is this result by Gupta and Penn, which says that you can maintain for any epsilon a 1 minus epsilon approximate matching with an update time which is root m over epsilon squared. How to think about this result? It's just generalizing that folklore algorithm I showed you before and extending it to the setting of sparse graph. Okay? So if your graph is dense, that is m is about n squared, you will recover the folklore result, which is n over epsilon squared update. Okay? And so this is just saying that we can exploit the sparsity and improve the runtime of the folklore result to root m over epsilon squared. What about lower bounds? Assuming a conjecture called the OMV conjecture, we know that if you wanted to compute exact matching, then for any delta greater than 0, we don't expect an n to the 1 minus delta update time. But this is for exact matching. And there are no barriers, no such barriers known for approximate or nearly approximate. So here is a question which is which this state of affairs highlights naturally. Is there an algorithm that allows you to maintain 1 minus epsilon approximate matching for some very small epsilon with an update time which is small O of n? And ideally, again, we would like to beat n here by some polynomial factor, but even the small O of n update time question is okay. So the starting point for the work that I'm going to describe is indeed these two questions. And our main results are that we make a very modest progress on both these questions, and ruling out that the current state of the art in terms of upper bounds is the right answer for these problems. If I wanted to be technically precise, I would have written very as a tower function of varies, as you will see in a moment, because the progress is indeed very, 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 I shouldn't go on, modest. And but I think one nice takeaway from from our work is a new approach for thinking about the matching problem, solving matching problem approximately in dense graphs, which is the notion of sparsifier for matching, and which may be of independent interest. Okay. So let me, yeah. No, so most of these results can be converted into, yeah, to worst case also. Yeah. Exactly. There are this standard. There is a standard trick. Exactly. You will do partial re. Yeah. That's a good question. I think it will hold for amortized, but yeah, I think it will hold for amortized also. Yeah, I think so. The streaming, yes, is for worst case. For random, we can get something like 2/3 approximation, or even like recently, I think there was a result which even reached 2/3 very slightly in n polylog space. Yeah, yeah. Okay, so what are our results? Well, the first result is that we can get a 1 minus small of 1 approximation to the matching problem in streams using space, which is n square over polylog star n. So that's why the very versatile function. And the algorithm runs in polynomial. So the way to think about this result is showing that there is something non-trivial between the two extremes, but the hope was to get to space which beats n square by a polynomial factor, but here the improvement is only a polylog star n. And then if you don't require the algorithm to run in polynomial time, which in the streaming model, you can just assume the focus is on space, then you can slightly improve the space bound to n square over 2 to the theta log star. For dynamic matchings, we can show that there is a fully dynamic algorithm to maintain a 1 minus small of 1 approximate matching with an update time, which is once again n over polylog star. The algorithm works even against adaptive adversaries. So an adversary can look at what you output and decide on the sequence of insertions and deletion. So what about the techniques for getting these results? Both these results follow from same technique, and which is basically a new sparsifier for preserving matchings approximately in dense graphs. And so we'll call this sparsifier matching cover. And roughly speaking, this object will preserve large matchings between arbitrary pair of subsets of vertices in the graph. Okay? Not just entire graph. You give any two large enough subsets which have a large matching, it will preserve it approximately. And so our main contribution is going to be to highlight that there is in fact an efficient way to build a sparse matching cover where sparse will be really polylog star n improvement over the naive representation using Szemeredi's regularity lemma. Okay, so the plan for the rest of the talk is I'll divide it into 3 parts, and hopefully I'll get to the third part as well. So the first part is going to be to formally introduce this notion of matching covers and show how we construct them. Second will be to show application of these objects to streaming and dynamic matching. And the last part, I want to show you a connection between matching covers and Ruzsa-Szemerédi graphs, and how the sparsity or the density of the best matching covers is in fact related to the question of resolving density of RS graphs. Okay, so here is how we'll define matching cover. So let alpha be any parameter between 0 and 1. Then alpha matching cover of a graph G is a subgraph H with the following property. If you gave me any two disjoint sets A and B of vertices in the graph G, then H preserves the size of the largest matching up to an additive error of alpha. Okay. So if you had a matching cover of a graph, you can output the largest matching in the graph to within an additive error of alpha. Now it may seem like that this is an overkill. After all, we care to find the largest matching in the entire graph. Why do we want a property which is preserving these things for arbitrary subsets A and B? It's not difficult to show that, for example, in the streaming model, if you wanted a good approximation, then want to beat factor 2/3, for example, then you really need an object which is able to answer questions like these for very large arbitrary subsets. Okay, so here is an equivalent way of thinking about this object and which is kind of a hitting set view of the problem. And this is going to be algorithmically more helpful to us, as you will see in a short moment. So what's the hitting set view? I'll define an alpha hitting set to be a subgraph H of a given graph T, which now has the following property. Whenever you graph T has two sets AB of vertices of size alpha n, which have a perfect matching between them, then the hitting set has the property that at least one edge that is connecting vertices in A to vertices in B is included in the solution. And it's not difficult at all to show that if you have an alpha hitting set, then you will also get an alpha matching cover. Okay, so all you need is to be able to hit subsets which have very large matching. Okay? And the proof really follows from Hall's theorem. Okay, so here is the result that I'm going to explain next, which is the tool we are going to use for both streaming and dynamic matching algorithm. So there is a randomized algorithm which runs in roughly n squared time and outputs 1 over log polylog star n matching cover, which contains n squared over polylog star n edges. And so this means if you have this cover, you can recover a maximum matching in the graph up to an additive error of n over polylog star. Now, existence of such objects was shown almost 10 years ago in a work in a paper I wrote with Goel and Kapralov. But it was shown only for bipartite graphs. So our contributions here are to show first they exist. These objects exist also for general graph, but more importantly, we give an efficient algorithm for constructing them. Okay? That was not known in the previous work. Okay, so how do we construct these matching covers? Okay. So our starting point is going to be Szemeredi's regularity lemma, and roughly speaking, for our purposes, what the regularity lemma says is the following: if you gave me any parameter epsilon, then I can do a decomposition of the graph where we'll put aside some epsilon fraction of vertices, but the remaining vertices after that will more or less have some very nice structure. And then we can hope to exploit this structure. So what is this nice structure? Well, the remaining vertices can be divided into k sets of equal size, where k is going to be some function of epsilon. And the nice structure is the following: all but epsilon pairs of Ci Cj are going to be regular. So what does regularity mean here? It means that if I take any Ci Cj which is regular, I take a set S of vertices from Ci, I take a set T of vertices from Cj, and assume for now S and T are both large, they are at least epsilon fraction of vertices in Ci and Cj. Then the number of, or the density of the edges between these two sets would be very similar to the density of the edges between Ci and C. So it's as if you can think of this as a random bipartite graph where the density of the edges in this random bipartite graph corresponds to the density between Ci and C. Okay. So large subsets will capture an edge mass, which is what you will expect in a random graph. That's what this regularity means. So we are going to set epsilon to be some 1 over polylog star n, and for this choice, our k is going to turn out to be something between 1 over epsilon and log. Now, what's our matching cover? It has a very simple construction. There will be two things we will do. Some edges in the graph we will just store without any modification or processing. and some other edges we're just going to sample. Okay? And you can almost guess from the structure what this is going to be. So we'll store all the edges which are incident on the noise vertices, and that's order epsilon n square edges. We'll also store all the edges inside each CI. That's another epsilon n square edges. We'll store all the edges between non-regular pairs. That's also epsilon n square. And then among regular pairs, the ones which are sparse, which means the edge density is order epsilon, I'm going to store those also. Okay? That just leaves dense regular pairs. And for them, we're just going to subsample edges at rate 1/log. And that will be n square over log n edges. And that's definitely order epsilon n square for our choice of epsilon. So the total number of edges we are going to store will be n square over polylog star. And we can. Yes, they won't even contribute that much. Yes. Yeah. But I have other sources of getting. Yes. Yeah. Yeah. Okay. So good. So okay. So now it's a simple exercise to show that this is going to give us something which is going to be a 4 epsilon matching cover of the original graph. Okay. So what do we want to do? We want to say, let's look at any two sets A and B of size 4 epsilon n, which have a perfect matching between them. We want to show that our cover hits these sets. So if there are any edges between these two guys which were outside of dense regular pairs, I already have them. I stored everything. So the only worry is that all of this M star, all these edge slots, they happen to be between dense regular pairs. And here, it's not difficult to show that randomly sampling edges at rate 1/log n will give us a hitting set for any large matching between a dense regular pair. Large is involving more than epsilon fraction of vertices in the dense regular pair. And moreover, it's going to be robust because not only I'll hit it once at this sampling rate, I'm going to actually collect an surplus of edges. So even if you deleted n square over log n to the 10 edges, I'll have still something left that will continue hitting this large set. There is one small worry that that might come up, that M star is only over dense regular pair, but the way it manifests itself is always by involving a tiny fraction of vertices. Okay. This cannot happen because I'm choosing 4 epsilon n. So you can actually do some pre-processing, get rid of all the ones which are using less than epsilon fraction of the CI vertices. Okay. So if you do that, you will be still left with 2 epsilon n, which will only be between dense regular pairs and appearing with large enough size that I can invoke this on. So that's it. It's as simple as this. We are going to spend some O tilde n squared time to construct this decomposition. And then we are going to just do this process to build a matching cover, which has n square over polylog star n edges and has a performance guarantee that it will preserve matchings to within additive error of n over log star. And the part about being robust to adversarial deletions, that's not going to play any role in streaming algorithm, but it will play a role in designing dynamic algorithms. Okay, so how do we use this? Sorry? Oh, that's the choice we need to be able to get control on the number of parts we create. This is what is needed. This is a consequence of the regularity lemma. Okay, so let me show you how this implies our results for streaming and dynamic matching. I think we had spent this is a while ago. We had spent a little bit of time at that time looking at this, if we could use them, and we couldn't. Yeah, we couldn't quite make it work. We might have missed something, but yeah, I think it's more like we could not make it work. It's not that we. Yes, absolutely. Okay, so here is the very simple application to the streaming matching. So we have a matching cover which has n square over log star n to the c edges. And what we are going to do is you have your input stream of the graph edges. I'm going to partition it into k pieces, and k will be log star n to the c over 2. Okay? The c is the same as the c in the matching cover. And for each of these pieces given to gk, I'm going to compute a matching cover. And in the end, I'm going to output union of all these k matching covers. Okay? So what's the space used? Well, I need n square over k space to process each gi. And then I'm going to compress it to a matching cover of size n square over log star n to the c. But I'm going to store k of them. So if you just, our choice of k is balancing these two quantities, and you will basically get n square over polylog star n. Same for the error. You will still walk away with an additive error of n over polylog star. That's additive error. I claimed in the theorems that we are getting multiplicative approximation, and that's rather easy to turn this additive error algorithm to multiplicative approximation. If the size of the largest matching, which is mu of t is denoting the size of the largest matching, if it is much larger than n over polylog star n, then my additive error is already a multiplicative error guarantee as well. But if not, then I know the number of edges in my graph is bounded by 2n times the size of the largest matching. So if the largest matching was not too large, I can simply store the entire graph. And it will take n square over polylog star n space, and I'll compute the exact. There is one additional subtlety here. Since we are making such small savings, we can't just store these edges naively, because then the number of edges times log n would exceed n squared. And so we have to rely on these succinct dictionary data structures, which basically can allow you to store these objects in space that is almost matches the information theoretic. Okay, so what about dynamic matchings? For the dynamic setting, the idea is going to be relying on the Gupta-Pang algorithm, which allows you to maintain a 1 minus epsilon approximate matching with about root m update time. And what we want is to make m small enough so that root m gives us the update time that we want. So we are going to feed a small O of 1 matching cover to the Gupta-Pang algorithm. And since it uses an update time of root m, we are going to get n over polylog star n update time. The question is, how often do we need to recompute this matching cover? So once you have a matching cover, for the next n square over log n to the 10 updates, anything you insert, I'll just add it to the matching cover. So things are going to remain good. And any deletions you do, I will delete it from the matching cover. But since our cover is robust, it can handle n square over log n to the 10 deletions. We are going to continue to maintain the additive error guarantee for our cover. And so with so many updates to recompute, we can easily amortize the cost of computing matching cover over these updates. We can actually handle fewer updates to amortized over it. And then getting a multiplicative approximation guarantee is a similar idea as before. And you consider dense regime and the sparse regime. And in the dense regime, our additive error guarantee is already a multiplicative guarantee. And in the sparse regime, we're just going to directly run the Gupta-Pang algorithm. We don't even need to go through matching cover. There are details and some technicalities in because as the updates happen, you can oscillate between dense and the sparse regime. So you need to pass control between these two regimes, but all those follow from standard. So basically, once you have the matching covered, these results, you can optimize some of the things I'm saying here, but they don't qualitatively change what you get. So they follow pretty much directly from the matching cover, these results once we have. How much time do I have? 10 minutes?
Yeah. But also
Okay. So I think if I have just 10-15 minutes, I want to talk about this last part. So then, good. Okay. So I think I want to spend just a little bit of a time telling you about an interesting connection between matching covers and RS graphs. So with what I've shown so far, it's clear that the performance of both our streaming algorithm and the dynamic matching algorithms are really determined by the size of these matching cover. In case of streaming, this determines the space I need. And in case of dynamic matchings, matching cover size determines what I feed to the Gupta-Pang algorithm. And my improvement is related to size of the object that I'm feeding to Gupta-Pang. So it's a natural question to ask, can we get, more sparse matching covers than the ones we are creating? And the answer is, as I've alluded already, is intimately connected to the problem of determining density of RS graphs. So what are these graphs? So I just need to define one thing before I introduce this graph. It's the notion of an induced matching. So what's an induced matching in a graph? It's a matching such that if you look at the endpoints of the vertices which participate in this matching, the graph contains no other edges besides. So this is an induced matching here shown in this graph. And basically, RS graphs are graphs whose edges can be partitioned into large induced matches, edge disjoint induced matches. Large is important here because edges of any graph can be partitioned into edge disjoint induced matchings if you consider matchings of size 1. So it's important to think. So with large, for large, just think omega n. Okay, that large. So here is an RS graph which has 4 induced matchings of size 3 each. So here is the first matching, another one, and another one. So the surprising fact about these graphs is that even though the induced matching property, especially if I require the induced matchings to be omega and large, they indicate, they enforce local sparsity, because wherever you choose to put this large induced matching, you can't have any other edge, right? So they forbid edges in all those edge slots. The surprising thing is that these graphs can still be very dense. So here is what we currently know about these graphs in the setting of very large matchings. So let me denote by RS of n comma beta the maximum number of edges you can have in an n vertex RS graph with induced matchings of size beta n, where beta is, think of it for now, maybe just a constant between 0 and 1. So what we know is that number of edges in such graphs is sandwiched somewhere between n to the 1 plus 1 over log n roughly, and n square over 2 to the theta log star. So there is a big gap, and once you go below, you allow matching sizes to be somewhat smaller than n, then work of Noga and others have shown that you can have graphs which have theta n square edges. In fact, I guess n square like n choose 2 minus small o of n square, right? Yeah, edges. Okay. So the challenge here is for the case when we are looking at size of the matching to be very close, proportional to the number of vertices to a constant, or something just slightly below a constant. Okay, so what's the connection to matching covers? So here is a result that was shown in my earlier work, that any alpha matching cover must have at least roughly as many edges as an RS graph, which has induced matchings of size slightly larger than alpha. So for any delta greater than 0, if you had an RS graph which had matchings of size alpha plus delta times n, the induced matching size, then whatever is the number of edges in such graph, that's the lower bound on the number of edges you need in your matching cover. Okay. And the idea is very simple. If you look at any induced matching, it has size alpha plus delta times n. In order to be a cover for just this induced matching, you need to store delta n edges. If you leave out more than delta n edges, then I will have a violating set. Okay. And I'm strongly using the fact that these matchings are induced. So that's it. It's just as simple as that. The interesting thing is there is a converse relation also. Okay. We showed this converse relation for bipartite graphs in the earlier work, and in the current work we show it for general graphs as well. And what's the converse relationship? For any alpha, you can build an alpha matching cover which contains roughly density of RS graphs with induced matchings of size alpha over 8. For this upper bound on the size of matching covers, unlike the result I just showed you, which had a fast algorithm for constructing matching covers, we do not know any efficient algorithm for constructing a matching cover which achieves this size bound. So this result essentially is what can be used to get a slightly better space guarantee for streaming algorithm, but you have to give up on polynomial time because we don't know how to construct such things efficiently. Okay, looks like I'm doing good time. So, okay, so let me then just conclude. And so we developed an new way of approaching the problem of maintaining large approximate matchings in dense graphs using this notion of matching sparsifier. The framework gives some very slight improvements over prior state of the art. And most importantly, I guess the two outstanding questions, which were the starting point for our work, and this may be especially of interest for students looking for problems, they actually remain, still open. The first one is, can you design a streaming algorithm that gives better than half approximation to the matching problem in n to the 2 minus delta space for any delta greater than 0? Just small polynomial improvement over n squared. There is no barrier which rules this out, and but it remains open. And I would say that at least streaming algorithms for graph problems, this is perhaps at this point the most prominent open question. And similarly, in the setting of fully dynamic algorithms, if you want to maintain better than 2/3 approximate matching, we don't seem to have any algorithms which can get us better than, much better than an update time. We can bring it down to n over polylog star n, but the goal is to bring it down to n to the 1 minus delta update time for some delta greater than 0. So I think that's all I wanted to say. I'm happy to take any questions. Yeah, I mean, you can get 1 minus approximate matching in number of passes, which are poly 1 over epsilon. Yeah, so I forget what is the exact dependence, but I think it is going to behave like poly 1 over epsilon. Yeah, and already in 2 passes you make some good gains over half. You can now start maintaining augmenting paths. Yeah. Oh yes. So for size. I in the dynamic setting. No. So okay. So you can get an O tilde 1 approximation to size in polylog n space if the edges are randomly ordered. But if you gave me edges adversarially ordered, we essentially do not know anything much better than maintaining a maximal match. No, because you need random access to do the exploration of the graph somehow. Yeah, in fact, that is another fascinating open question. Can you do in n to the 0.99 space polylog n? Just the estimate the size. Yes, it's open. Yeah, and the random order result, we had it almost 10 years ago, and we thought this will open the way for something interesting, but we didn't succeed. Yeah, and yeah. Sorry. All these results, no advantages emerge. Yeah. In fact, if someone wanted to think about these problems, I would say just think about the bipartite case. We don't know anything better. Yeah. So the challenge is not bipartite persistence. Any other questions? All right, thank you.